Alright, welcome back everyone. In this video we're going to continue our conversations of Mohr's circle. In case you wonder what the guy looks like, this is Otto Mohr, picture of him, a civil engineer right down there. And I wanted to add a little extra information in case you were interested. Instead of drawing the circle, you could develop some equations. So here are some equations for if I have a stressed element with a sigma x, sigma y, and a tau xy, and I want to rotate it some angle theta, and I want to know what my new stresses are. I have these series of equations where my sigma x prime, the new stress, you can see that big long ugly equation, sigma y prime, tau x prime, y prime, all those are the rotated, after it's been rotated that theta degrees. Sigma 1 and 2, which are our principal stresses, and the tan 2 theta s. Now when I say theta s, what I mean is the angle to get to the maximum in-plane shear stress, that vertical piece. There's also a theta p, that's the angle to get to the principal stresses. So that's what those subscripts mean in that case. So you can use those equations as well. Also, maximum in-plane shear stress, we said that's just the radius of the circle, or that is the equation for the radius that we see right about there. So I'm not a big fan of memorizing these equations, and I think they can be kind of cumbersome because if you need to solve for, like what we did last time, where you need to solve for the angle for the maximum stresses or something like that, you have to rearrange it, do a lot of rearranging. I think it's easier just to use the equations use Mohr's circle instead of the equations. Go about that route. But today what we're going to talk about, everything we've done so far is in 2D. Today we're going to talk about 3D Mohr circle, or in particular, what we're interested in are the principal stresses. So what we were looking at last time was an element with two principal stresses on it. And we called those principal stresses sigma 1 and sigma 2. Now what that actually looks like, if we were to look at the third dimension, is something more like this with our cube. So that's what it looks like. It basically just drawn it in 3D, or if I were to twist it slightly. I don't have any information on that third face, but for the time being, let's say that third face, let's say the principal stress is 0, or there's no stresses. And that's usually actually the case, because if it's on the outside of a surface, then there is no stress. But so if we were to map this out on Mohr's circle, starting with the way we had looked at it last time with these principal stresses, I end up with something like this, where we said we had a sigma 1 and a sigma 2, and those were my principal stresses. That's our 2D element. That's what we've already seen. Now the only thing we're doing here to look at this third dimension is to add another principal stress, and in this case we said it's equal to 0. So now I have 3 points. I have one at 0, sigma 1, and sigma 2. I can call this third stress sigma 3. And because I have 3 different points, I can actually have 3 different circles. I might have a circle between 2 and 3, something like that. I'll make a different color so it stands out a little bit, maybe red. And I could also have a circle between 3 and 1. Now, because I have 3 different circles, I have 3 different radii for those circles. And if I look here, what we talked about last time was that the radius is equal to our maximum in-plane shear stress. Well, the only difference here is what plane is that? So between sigma 1 and sigma 2, we can see that's our sigma x and our sigma y plane, right? I mean, that's where we started off. I can see this is the x direction and y direction. So between 1 and 2, this would be tau xy. Now I have a radius for this smaller red circle over here, and I'd say, well, that's between 2 and 3. Well, I see 2 is the y direction, 3 is my z direction. So this would be tau y z. And then lastly, I also have one more radius, which is this big guy for the purple one between 1 and 3. 1 is the x direction, 3 is the z. So this would be tau x Z. So if I have three different radii I can compare, what's the largest one? So the largest one will be the absolute maximum shear stress for this element. And clearly that's the XZ. All right, so let's go ahead and talk about the process for how you are going to solve these problems. First step is looking at your 2D element just like last time. What you're going to do is you're going to find your 2D principal stresses. And hopefully you remember, I mean, I guess suppose you could just use these equations at this point, right? But really what it is this is your radius over here, and this is my sigma average right there. So it's just your average plus or minus the radius to get those principal stresses. And after I have those two principal stresses, then the second step would be to put those onto Mohr's circle. And after I have the Mohr circle drawn, I'll have a single circle with two principal stresses. Then I can add that third stress or a point, and that point will be on your sigma axis for your sigma 3. And after I have the 3 points, then I could draw my other two circles. And finally, what I can say is this absolute maximum shear stress is just the radius of the largest circle. So if I had to write an equation for that, it would look like this. Tau max, before I had a in plane, but these are absolute, and it would just be the maximum of the radii, which is sigma 3 minus 2 over 2 if it's between principal stresses 2 and 3, or so on and so forth for the others. All right, so let's take a look at a quick example and then be done with it. So let's say we have a situation that looks like this. So what we have is an element. I can see that it has 30 megapascals in the sigma y direction. In compression, I have 90 megapascals in my sigma x direction. Of course, this is assuming standard notation of x to the right, y vertical, z coming out to me. And that is actually a negative 15 megapascals in shear. So those are my three stresses. I'm given that the third one, the one I can't see, the one that is on this face towards me, says it's 40 megapascals in compression. So if I had a 3D cube, I would see it pushing on that third face. So where I want to start is looking at Mohr's circle for the 2D element. The way I like to start this is I start by finding the average stress, and I find that to be 30 megapascals. That's in essence the center of my circle, and the radius. And for the radius, I ended up with something like 61.85 megapascals. Because once I know where the center of the circle is and the radius of that circle, then I know my principal stresses, sigma 1 and sigma 2, would be the center plus or minus the radius. So I have 30 plus this 61.85 gives me 91.85 megapascals. And my sigma 2, I have 30 minus 61.85, or minus 31.85 megapascals. So finally, I can look at what look at my Mohr circle for this thing. So one stress is at 91, maybe about here, 91.85, and another one is at negative 31, maybe about here. So I can draw my circle between those two. And there's my Mohr circle for the 2D element. Now I need to add in that third sigma 3, and I'm given this third sigma 3 is 40 megapascals in compression. So compression means negative. So actually I'd be about, I don't know, we'll put it about here, minus 40. Not much room in here. Let me move this. And so that means I can then draw my other two circles between these 3 points. And you probably didn't necessarily need to draw the 3 circles in order to find out that maximum. Maybe you could have used the equation, but what I can see is my maximum absolute shear stress is the largest radius, or the distance from that 91.85 down to that 40, or the distance between those points is 65.93 megapascal. So I hope you found that example helpful. There are another example or two in the notes, so take a look at those as well. Give the homework a shot. Let me know if you have any problems. Keep up the good work, and I'll talk to you all later. Bye.